Welcome back to ECE 501B. Several things are finishing rather quickly. The class assignment will be completed on Wednesday of this week. Our final exam will be a week from today. I'm going to get my final exams confused, but the final exam in this class is a week from today, although it's minus 30 minutes. You will need to make sure that you are here 30 minutes before you normally are here for next Monday's final. Teacher course evaluations are due this Wednesday at 11:59, and it would be helpful if you could fill those out if you haven't already. I don't have a way of monitoring who has or who has not completed their teacher course evaluation, but hopefully you will do that so that I can get some feedback on the course. There is some final exam review material on the D2L website. I think it's at the bottom of the content page, maybe even below your project assignment unit on the content page. But if you're interested, you can look at that. There's some notes and a video from a previous semester that basically goes through the material that will be there for you on the final. And what did I say last time? Maybe 8 problems for the final exam, and maybe I'll put a little bit more about that, but I think that's also discussed during that final exam review. We'll try to be consistent with that, and I think you get 4 pages of notes, and maybe you've had 3 pages of notes up to this point. Today what we want to do is start the second book of the semester, or the second textbook for the course. We may not get all the way through that textbook, but at least we will get a start, and you will start to see the connection with the finite dimensional material that we've covered or worked on, and this infinite dimensional material, which is covered through the idea or the concept of signal theory. And that's the title of the book by Franks, and that's under the course resources on D2L, that particular PDF of the book. To start that material, we will work through a motivational example. Maybe you're not used to hearing convolution as a motivational example, but we will talk about convolution as linear operators, and then if we have time, we will start getting into this idea of signal sets. We started the course with sets of vectors, and then we established a way of determining a distance or a metric relative to those vectors. Now we need to think about signals, and how do we establish a distance between signals that might belong to the same set. And that's where we are headed for the material in Franks, which is signal theory. And that's really this particular material called signal theory, or that's the title of the book, is a subset of a more general topic, functional analysis. And what we want to do now is try to motivate that material and discuss it so that you can, if you so desire, start getting up to speed with that infinite dimensional material using the foundation that you already have from the finite dimensional material that we've covered so far in this class. Here we are going to be thinking about signals, and the way that he is presenting the idea of a signal is typically when we have a signal that's carrying some kind of information. And Franks is coming from a communications perspective, and there he might be interested in how do we communicate with signals and how do we transmit information with signals. But we are thinking of these signals in this context of carrying information. How do they carry information? If we start talking about signals, we might be thinking about the way that we have classified signals in the past. If you've taken an earlier class as an undergraduate student in electrical and computer engineering, you might have thought of classifying signals, for example, as energy signals or power signals. And we also, so once we have them classified, or if we classify signals, we also might want to know how are these signals represented. In Frank's, what he's interested in is he's trying to look at signals from a signal space viewpoint. Again, we've been talking about a vector space viewpoint up to this point. Now we're trying to sort of see this analogy between signals and vectors. How do we group signals so that we can create this signal space viewpoint? And with that viewpoint, we're trying to look at signals now from a more geometrical concept. Instead of just this wiggly line as a function of time, can we now classify these wiggles or these functions in a geometric way so that we can talk about distance between them? So this signal space viewpoint provides a geometrical view of not only signals, but also of the way that we might process these signals. These signals might get processed maybe in sort of a implicit way when we start transmitting a signal through the airwaves. That's now going through a channel, and we've actually somehow modified that signal from point A to point B. That's now done some kind of signal processing. How can we now put a geometrical perspective to not only these signals, but also these signal processing operations? Or what if we want to filter a signal? That's a signal processing operation. We may want a low-pass filter. We may want a high-pass filter. We may want to do something else with this signal. We may want to add them up. We may want to try to take an inner product. How do we treat those from a geometrical perspective? Dealing with this new textbook, chapters 1 through 5 are really laying the foundation. And the other chapters, 6 through 10, are more application related. We have 2 lectures left, so we'll take this lecture to cover the first half of the book, and Wednesday's class will do the second. So you have just a little reading to do between now and Wednesday. No, we will probably only get into the first 2 chapters of this textbook, but that will hopefully allow you to start seeing the connection with infinite dimensional concepts and the previous material that's built up the foundation on these ideas in the finite dimensional setting. Let's just sort of point that out explicitly. Our previous material dealt with finite dimensional spaces, these r to the n, c to the n's, etc. Now we want to extend that into these infinite dimensional spaces. Let's now look at that from a, let's say, a general introduction and motivation perspective. Let's take, just for illustration purposes, something that we've been dealing with up to this point, some list of numbers. And you can just think of a list of real numbers. Consider a list in the following form, and we could collapse that entire list into some variable x, but now our list is, let's say, x sub 1, x sub 2, and you could think of these made of real numbers. Each coordinate in this vector is some real number. And now let's take that list form and plot them. Meaning now for specific values of little n, let's just take little n equal to 8 for starters, and now plot each of these coordinates relative to, let's say, an indexed line on the horizontal axis. And now I'm running out of space. And we could think of different points or numerical values, real numbers at each of those coordinates or in each of those positions of that list X. And you sort of see this shape. If we now start to sort of back out from that and make our resolution maybe a little bit finer, with n equal to 16, for example, and again plot x sub I, and you can do a better job of it than I can, but eventually you see this same sort of shape. And as we let little n get larger and larger, and in the limit as n goes to infinity, we start to get a smooth curve or a function. As n goes to infinity, and let's say we keep zooming out, this vector x, or this entity x, starts to look like a function. Meaning now we have something that maybe does that between the endpoints. And we now have this x of t, and maybe we no longer have discrete points on the horizontal line. Those have now collapsed into a continuous set of values on the real line, so that now as n went to infinity, the index I goes to this continuous variable t, and x sub I now, these coordinates now have been all moved into some function x. Now we have an x. As we zoomed out, we had more and more points on the horizontal disk axis. So now we have an infinite dimensional vector space. Which might be called, for Franks, that might be called a signal space, or someone else might call it a function space. And once we have this new idea, this infinite dimensional object, we can actually perform our familiar operations on it. We can do some linear operations, or with linear with standard definitions, of addition and scalar multiplication. With that available to us, now many of these results that we had in the finite dimensional case can move into this new signal space that we've now identified. Many results from the finite case apply directly. And one of the concepts or results that we had before was this notion of eigenvalues and eigenvectors, or these invariant subspaces, or these invariant vectors, these x sub i's. Now let's see if we can, and when we were talking about eigenvectors and eigenvalues, those were associated with a map, or a more specific map, a linear operator that operated on or took a vector from one vector space back into itself. So now let's look at linear operators in that context and eigenvectors. And these vector representations. Again, these vectors belong to sets. These sets had vectors in them. These vector representations in terms of eigenvectors, so that we could actually represent any vector in our space. We could decompose it in terms of the eigenvectors that we've maybe identified relative to these operators. I give you an operator, and you can now take that operator and find eigenvectors and eigenvalues for that operator. We want to be able to do the same thing, and once you have eigenvectors, you can now decompose any vector in that set in terms of a linear combination of those eigenvectors. We want to think about doing that for an infinite dimensional setting. What do we mean by an operator, and what do we now mean about relative, or what's analogous to an eigenvector? Now maybe that's an eigenfunction. And now is that eigenfunction invariant with respect to that operator? And if it is, what does that mean? Well, that means that if we operate on that eigenfunction, we maybe get back that eigenfunction just scaled by some value or some scalar, which is now an eigenvalue. That's what we've been doing with these finite dimensional concepts. What I'm saying is, let's remind ourselves or recall the eigenvector equation, and this you can immediately write down. As soon as I say the eigenvector equation or eigenvalue eigenvector equation, you see something mentally after this semester. You now know that that maybe means t, v sub I, is equal to lambda sub I, v sub I, where v sub I are these invariant directions that we stay in that direction when we operate on it with that particular operator, t, this linear operator t. We want to now think about this idea or this concept in an infinite dimensional setting. Let's now consider what this would look like in this infinite dimensional setting, which now instead of eigenvectors, we're going to call those eigenfunctions. Since we no longer have, let's say, these finite dimensional vectors, we now have functions that we saw forming when we zoomed out from this list that just continued to get more and more coordinates in that list. Now we might have a linear operator t, which operates on some, let's say, eigenfunction u sub I of t, that will then result in staying in that same direction or in that same eigenfunction, just scaled by some scalar lambda sub I. Here is now our linear operator t. U sub I is now our ith eigenfunction, and lambda sub I is our ith eigenvalue. And to talk about this, let's look at something that I'm assuming that we are all somewhat familiar with, which is convolution. Let's now consider and we're going to call that now an operator. Consider an operator you're already familiar with. And let's restrict our discussion to a linear time invariant system. And that now allows us to think about a operation, or what we've come to learn about system behavior, which is this convolution. And a convolution is really just what happens to a system, or I'm sorry, a signal, when we apply it to a system. We get some output out of that, and the system, how that system treats that input is shown to us by the convolution. How it shapes or how it redirects the output is all a result of this convolution operation. In terms of expression, we have y of t is equal to, let's say our variable of integration is tau, and let's go ahead and let tau go from minus infinity to plus infinity, x of t minus tau, h of tau, d tau. That's now our familiar convolution integral that we're used to seeing, where now h of tau might be the impulse response of some system, x is our input, and y is the output. And now what we want to do is say, well, let's just call that some operator t operating on x of t. This is now our linear operator notation, and it's taking an input x of t into an output y of t. That's this notion of a linear operator. And you may be familiar with that in a more diagrammatic setting. You might remember what happens in a block diagram picture where you now have the input x of t. The block now is your system, which might have an impulse response h of t producing some output y of t. But even in this block diagram, we can think of this operation that happens between the impulse response and the input to generate the output, and the input itself is some function, and so is the output, but those are living in the same space, so that this operator t is indeed an operator consistent with how we've defined operators. It takes a vector and returns the output back into the original space that we started in. So this is an operator because both x of t and y of t are in the same space. And now what we want to do is see if there's, and when we were dealing with eigenvalues and eigenvectors, why did we sort of like those eigenvalues and eigenvectors? What did that tell us about that operator? That's a pretty vague question, isn't it? But it told us something, the eigenvalues told us maybe something about the dynamics of that system. If it was a, let's say, a physical system, we might like to look at the eigenvalues, and they now tell us something about the dynamics. The eigenvectors sort of tell us how things are shaped relative to those modes or those dynamics of the system. In this case, and if we'd identified eigenvalues and eigenvectors, we could actually do a transformation so that those eigenvalues in the ideal case are all on the diagonal. And now we have this nice matrix representation of this operator. And we might want to think about the same thing here. Is there a way to sort of decompose or represent that operator, or how does that operator work in certain directions? We know how the operator in the finite dimensional case functions in certain directions relative to these eigenvectors. It stays in that invariant space. Can we find similar eigenfunctions for this convolution operator? Let's make a claim. The claim is that e to the I omega t is in fact an eigenfunction of this operator t. And e to the I omega t, maybe it looks weird, but that's just, think of that as sinusoids. For a fixed omega, that's now some sinusoid. If you looked at the real part of e to the I omega t, if you remember Euler, e to the I omega t is just cosine omega t plus j or I sine omega t. So this is just a bunch of sinusoids, e to the I omega t for a fixed omega. Now let's check that claim to see if in fact e to the I omega t, or these sinusoids, do allow us to have eigenfunctions associated with this convolution operator or this linear operator capital T. Check. So let's now let the input be x of t equal to e to the I omega t. In our definition for the output y of t, that was this integral from tau equal minus infinity to infinity of x of t minus tau. Now we have x expressed as e to the I omega, but now we have t minus tau instead of t, h of tau d tau. Our variable of integration is tau, so any other variable we can sort of pull out of that integral. Let's now separate that complex exponential into two pieces, since the exponents can allow us to do that. And we now can rewrite this as this integral from tau equal minus infinity to infinity of e to the minus I omega tau h of tau d tau, and we'll pull out of that integral e to the I omega t. That's a variable that's not a function of tau. But this is now the structure that we wanted. We wanted now to have, and if you computed this for a fixed omega, fix a frequency, now you can evaluate this expression and get what? A scalar. Now you get some scalar out of that, and that will now weight this function e to the I omega t, which is what we were using as our input x of t. So we hit this system where we applied an operator, which is this convolution operator. We used that operator on this input, x of t, and the result ended up in the same direction or in the same eigenfunction that we started with, e to the I omega t. This is now remains our eigenfunction, which is now scaled by some scalar. And that is then giving us our output y of t. Or we could say, so t, that's our operator, applied to e to the I keep wanting to say j since I'm an electrical engineer, but this is now e to the I omega t, is now, let's say, some scalar that's maybe parameterized by omega. We pick an omega, and we can evaluate what's inside that square bracket, but that's now just some scalar lambda of omega e to the I omega t. And if that's the case, we've now actually defined what that scalar is. So now, what is this scalar going to be? If we look at this, if we now call that lambda of omega what's in square brackets, that's going to start to look very familiar to us. Now, if we simply make that definition, that's now this integral from tau equal minus infinity to infinity of e to the minus I omega tau h of tau d tau. And if you've taken earlier engineering classes, you go, oh, that's just this transfer function of omega, is one way of viewing it. Capital H of omega. That's now just some scalar. If you give me an omega, I can give you a number or a scalar, H of omega. And that's what we've now found is what? This is consistent with our eigenvalue. You give me a frequency, and I'll give you a capital H. I feel like I'm going to game. Give me a W. H of W. Where H of W is now this eigenvalue. And that's now, but now W is a continuous parameter. If you just looked at discrete values of frequency, then you would start to see this sort of eigenvalue, eigenvector, finite idea. But now, since it's continuous, we need to, instead of summing that, we're now integrating, or the summation process is this integral. So that now we have a way of thinking of this operator, this convolution operator, as t of e to the I omega t is now h of omega e to the I omega t. Where what we want to remember is that moving into the zooming out on that list of numbers allowed us to transition from this coordinate of numbers, or this finite number of values, into an infinite or continuous stream. So remember, moving to continuous caused the indices, these i's, to become continuous as well. And these eigenfunctions, the e to the I omega t, are now indexed by this continuous parameter omega. And we could now think of this block diagram again. Whoops. Let me just call this our linear time invariant system. Our input is a specific sinusoid, e to the I omega t, or it could be just labeled as u of omega of t, and that now generates some h of omega e to the I omega t, or that's now some lambda of omega u of omega t. And in this particular situation, how many eigenfunctions do we have? We have an infinite amount of those, don't we? We now have an infinite number of eigenfunctions, these e to the I omega t. That's just our frequency, or our index on frequency. So we now have an infinite number of those eigenfunctions, in contrast to what we've been playing with this semester, which is some finite number of eigenfunctions or eigenvectors. And so now we can interpret this the transfer function this h of omega as the eigenvalue spectrum, since it's now continuous in nature with respect to frequency, as the eigenvalue spectrum of this operator t. And now that spectrum is giving us a weighting, magnitude, and angle of these different eigenfunctions. You give me a frequency, and now h may be different for each frequency. And that's true for an infinite number of eigenfunctions. So now we've decomposed this operator into an infinite number of eigenfunctions. We can now write any function in terms of these eigenfunctions. That's the idea. Meaning, when we were dealing in the finite dimensional case, if I gave you a complete set of eigenvectors, you could write any vector in your vector space in terms of those eigenvectors. We want to do the same thing here. Now let's recall the importance of eigenvector decomposition for analyzing operators on finite dimensional vector spaces. Meaning, if somebody gave you a vector, you could decompose that vector in terms of some weighted sum of eigenvectors, where we might say, oh, that's A sub I, E sub I, summing over a finite number of eigenvectors E sub I, where V is some arbitrary vector that we're now writing or written in terms of this eigenvector basis. If that's the case, now what happens when we process that through this operator T? What happens when we look at TV? Now we have T operating on this sum of A sub I, E sub I's. A sub I's are scalars. Those can come out of the summation. Now we have this sum of T E sub I's. T is a linear operator, but these E's are special relative to that operator. They're eigenvectors. So now when we operate on these eigenvectors with this operator T, we stay in that same direction, E, and the only difference is we now get scaled by some lambda, some eigenvalue in that direction, E. Meaning we can now replace this right-hand side, T bracketed with this decomposition of the vector V, as a sum of A sub I, and now T E sub I becomes lambda sub I E sub I. And that allows our analysis to actually be simpler. Now, instead of worrying about all of these matrix and linear combinations with this operator, now, because we're dealing with eigenvectors, all we have to do is stay in that same direction and get scaled by an amount lambda for each of these E sub I's. And that allows us then to have a very simple process that results by decomposing any vector in terms of these eigenvectors. A very simple process results from using eigenvectors as our basis. Now, as a review for the final, how did we find these A sub I's relative to a vector V? If we want to decompose V, a generic vector, into its decomposition written as some linear combination of these eigenvectors, how did we find these coefficients that scaled these eigenvectors. Those were our inner products, weren't they? Or projections of our original vector v in the direction of each of these eigenvectors. So to find those coefficients, we could just take these projections or these inner products. And how did we get those coefficients a sub I? You just told me those were these projections. But now if we have this generic or arbitrary vector v, we can look at these inner products or projections a sub I as simply v inner product with each of the e sub i's. And each of these e sub i's are orthogonal for certain operators. And that makes it easy to think about what's happening relative to these coefficients a sub I. Let's now look at what happens in the continuous or infinite dimensional case. So what happens, now we might want to decompose this convolution operator in terms of these eigenfunctions. And we want to know, how do we weight these eigenfunctions for this convolution operator? What happens in the continuous or infinite dimensional case? And let's call that now a sub w, where we have some generic signal x, and we want to now find the inner product with these eigenfunctions, u sub w's. And what did we learn those eigenfunctions were for the convolution operator? Those were these complex exponentials, e to the I omega t. Now, if we're dealing with functions, we haven't yet specified what that inner product is, have we? But there is sort of a convention to the inner product of functions. Suppose we define that to be an integral over some time horizon. Let's just say it's from minus infinity to plus infinity. That's now a of t times the complex conjugate of b of t dt. So let's just say that's our inner product. If that's our inner product, now we can look at what or how to find these coefficients a sub w that lie in the direction of these eigenfunctions. Now a sub w is this integral from, let's say, t equal minus infinity to infinity of x of t e to the, and now the complex conjugate of e to the I omega t is just minus I omega t dt. And we've seen that before. So now that these coefficients we can find from this integral. And x of t. So now that gives us these coefficients that x of t is going to be decomposed in, and those coefficients weight the eigenfunctions. So now we have a way of rewriting x of t in terms of these eigenfunctions and these coefficients a sub w. And x of t can be written as weighted sums of these, let's say, u sub w's. I need to quit using so many exclamation points. It's not that exciting, huh? Although you give me a w, what do you give me? An h of w, right? Or now an a of w. Now we're giving these coefficients in terms of these directions, or how is x, the input signal, correlated with these sinusoids. So that now we can write x of t as a weighted sum of these eigenfunctions, and since we have an infinite number of them, the sum is now this integral. So x of t is a generic waveform, which we're viewing as the input to this convolution operator, and we're calling that t, capital T. So x of t is just an arbitrary waveform. Now we can rewrite that as this integral of weighted eigenfunctions. The weights are these a sub w's. The eigenfunctions are e to the I omega t, and we're now indexing over the frequencies, so that we now have this sum from omega of minus infinity up to plus infinity, and this is now an integral because we've now taken the index I to the continuous case. So we now have an integral because it's now a continuous expansion relative to frequency W. Where if we compared that with the finite dimensional case, there we might have had this V, which was this sum from A sub I, E sub I equal 1 to N, and now we have this infinite dimensional version of our input vector x in terms of this weighted collection of eigenfunctions. And now we really have two different sort of ways of breaking this signal apart. We also have the A's, don't we, which we might in earlier classes have called some capital X of omega, sort of the frequency domain version of this signal. Capital X of omega is now these coefficients, so if you give me the coefficients, I can now tell you what that signal was. So those are the A sub w's, which we were now saying were this integral from t equal minus infinity to infinity of x of t e to the minus I omega t dt. Where these are now the coefficients of our signal x of t in the frequency basis w. So these are now our weighting values. That's x of omega, and if you wanted to not go to the continuous case, you could just pick out a finite number of those frequencies and look at what's my weighting for these particular frequencies. And we also could think of x of t coefficients of x in the t basis. So that now we have x of t as this integral from omega equal minus infinity to infinity of x of omega e to the I omega t, d omega. And this is what we were saying were those I of omegas before. And now we have sort of two ways of thinking about the signal. We could either think of it in terms of these coefficients in the frequency basis, or these coefficients or weightings in the time basis. Yes? So now the question is, shouldn't there be a 1 over 2 pi or something floating around in there? I've sort of buried that with the omega. So the omega is now in radians, and I don't have to worry so much about t and frequency. So I've sort of collapsed that 2 pi away from here, and now I just have this maybe cleaner way of relating these two expressions for these coefficients, capital X of omega and little x of t, as far as how we can write those or express those. So this is telling us what? This expression is really telling us how much of the signal x is in the direction of these eigenfunctions. This is the projection. This tells us sort of the frequency content of our signal, capital X of omega, and the other uses that information to tell us how do we get back the time domain generic or arbitrary input signal if somebody specifies or tells you what's happening at each frequency, capital X of omega. Now you can build that up by recombining those with respect to each of the eigenfunctions, e to the I omega t. And that's how these capital X of omega and little x of t are sort of related. We can also relate those in terms of time domain and frequency domain relative to what you've learned already in earlier classes. Meaning, if we start with y of t, let's say is this convolution integral from tau equal minus infinity to infinity of x of t minus tau, h of tau d tau, that's this convolution in time, meaning you give me an input and a system. The system now is described by this impulse response, h of tau. I can now tell you, and from a time domain machine, I can now tell you what the output is going to look like. But you can also say, well, I don't have it in the time domain, or I want to do it differently. And now you go, I thought that convolution in the time domain was equivalent to something in the frequency domain. And you probably remember that cheer. Convolution in the time domain is equivalent to multiplication in the frequency domain. So this better be the same or equivalent to. In another way, you could say, well, y of t, I can, if you give me the frequency content or the eigenvalues of y in the frequency domain, the capital Y of omega, I can then tell you what y of t is. But a way to generate that capital Y of omega is to take x of omega, basically the representation of x in the frequency domain, and the representation of the system in the frequency domain, the h of omega, combine those to get y of omega. Meaning, we now could think of this as x of omega. That's just how x of t is decomposed in the frequency space. H of omega, which is how the system responds or how its frequency content is determined from its impulse response h. This is now, if this is what it's supposed to be, this should be y of omega, but if we have y of omega, we can just use those as coefficients or weightings on e to the I omega t d omega. So that now y of t is related to, so that we now have this multiplication in the frequency domain, and that's because we've now decomposed this relative to its frequency content. Because e to the I omega t is an eigenfunction that we can now decompose these signals into. So let's now see if we can actually show that this relationship is in fact true. Can we show from how we've defined the x of omega and h of omega, and in terms of x and h, little x and little h, can we actually show that that relationship that we've learned, that convolution in the time domain is consistent with multiplication in the frequency domain? Let's now see how that can come about from what we now know. Y of t then is this integral from, let's say our variable of integration is tau, tau equal minus infinity to infinity, x of t minus tau, h of tau, d tau. That's now equal to, now let's rewrite h of tau, or write that in terms of its weighted eigenfunctions. So we're not doing anything with x right now. We're just saying that's x of t minus tau. But we do have another way of expressing h of tau. We can rewrite h of tau in terms of a weighted combination of its frequency content, which is h of omega e to the I omega, well, here let me do it tau, since it's h of tau, I omega tau d omega from omega equal minus infinity to infinity d tau. And now we're not going to get too hung up on moving things in and out of integrators or integral operations. Let's now just exchange the integrals. So let's now slide everything inside the frequency integral, so that we now have this integral from omega equal minus infinity to infinity. And we also have this integral over tau from minus infinity to infinity of x of t minus tau, h of omega, e to the I omega tau, d tau, d omega. And let's clean this up, or try, with a change of variables. I don't like that x with an argument of t minus tau. I want that to just be x of something. So let's let that new something be sigma. That new argument of x in the time domain, let that be t minus tau. So that wherever we see a tau, that can be written as t minus sigma. And if we looked at d sigma, and if t is fixed, tau is, or d sigma is then minus d tau. Now can I slide that a little bit, whoops, and give myself enough room to write what I want. Now let's rewrite that using these new replaced variables. We didn't do anything with omega, That can stay the same. But now we've replaced tau with sigma. So when tau is minus infinity, what is sigma? If tau is now going from minus infinity, but sigma is now minus tau. So this is now sigma going from infinity to minus infinity. The way that we've basically sort of negated the sign relationship between sigma and tau. We now have x of sigma, h of omega, e to the I omega, and now we've made this a little more involved, but we can separate this exponential now a little more easily than we can separate x. So this now becomes e to the I omega t minus sigma. D tau is now minus d sigma d omega. Now we can start playing with, if I want to negate or if I want to flip my limits on the integration, I can change the sign of my integral, and I have a minus sign to play with, meaning I can now keep this omega the same. But now let's say, have sigma going from minus infinity to infinity, which means that my minus d sigma just becomes d sigma. I have x of sigma. Let me just keep inside the e to the minus I omega sigma, d sigma, and now I'm pushing everything else outside of that inner integral, which is h of omega, e to the I omega t is left over, d omega. And this is just how we defined x of omega. So that now we can write this as we said we were going to. This is this integral from minus infinity to infinity on omega of x of omega, h of omega, e to the I omega t d omega, where y of omega, the frequency content of our output, is simply found by multiplying these two transforms, h of omega and capital X of omega, which really says that we've now allowed ourselves to look at Fourier analysis maybe differently. Now we can think of it as similar to eigenvalues and eigenvectors. So all of Fourier analysis I don't know if I should be so bold, but I'll put it in parentheses, is just a trivial result from expansion in eigenfunctions of this linear time invariant operator. Meaning we can now think of Fourier analysis as sort of decomposing or taking projections. How does this signal x, how is it aligned with these eigenfunctions, which these eigenfunctions are just sines and cosines? How is our input aligned with these sines and cosines? And that will then allow me to obtain a way of decomposing this vector in terms of that frequency content, capital X of omega. where our key point is that x of t and capital X of omega, those are just different ways of representing the same thing. Little x of t and capital X of omega are just different representations or expansions in different bases, of, let's say, this abstract signal x. Yes? I'm sorry? So now what we are doing, if we were being correct in our analysis, now if we have a block diagram, the question is, what's happening in this block diagram? I'm used to multiplying things when I have a block diagram. Well, what you're doing really is you have now decomposed your signal in these eigenfunction directions, or in terms of sines and cosines, and you now have a capital X of omega. So you've moved your input into the frequency domain. You've said, I want to just look at this input in terms of its frequency content, or in terms of these eigenvalues, this capital X of omega. If I do that, then if I play with my system in terms of its frequency content, h of omega, how does it behave as a function of frequency? And you can get that from the impulse response. You can now say, oh, this impulse response can be thought of in terms of its frequency components or its eigenvalues. Now you're in both cases, in the system and the signal, you're in the frequency domain. That allows you to just multiply in the frequency domain to get the resulting components of your output as a function of frequency. And you know how to recombine those or weight those with these eigenfunctions to generate the time domain expression for your output y of t. That's just this inverse transform, the way that you've maybe learned it in the past. But really, this is now just a way of projecting these generic input signals in the direction of these sines and cosines, or in these sinusoids. And from that content, you can now play maybe more efficiently in the frequency domain, which is what we sort of like to do as engineers. And then if we need to, go back into the time domain at the end of all of that. That help? So this block diagram here, we're simply illustrating it for one eigenfunction, but in general, we now say, oh, what's going to sit over there in the frequency domain is a decomposition of our generic input in terms of its frequency content. And those are these coefficients, or these scalars, or these eigenvalues. That's capital X of omega. And we can do the same thing. Now we've, in a sense, we've started to represent signal operations, our system, and signals in the same way, as sort of this same set, these x's, capital X of omega and h of omega. We now have them living sort of in the same area or set, and it'd be nice if we could somehow put those into a format that we can start to measure distances with respect to. And that's where we want to go. So we are covering 10 chapters in 2 days. I can now cover this one concept in 1 minute. We now want to talk about signal spaces, or what did we have before? We had sets of elements that we called vectors in some vector space. Now what we want to do is create a place that we can collect these signals. That's going to be this signal space. And once we're in this signal space, or once we've defined a signal space, can we somehow measure geometrically or put some geometrical concepts? So now we might want to have a metric. You have a signal, I have a signal. How close are they? Or is one bigger than the other? Or how do we compare these? And that's where we will try to go on Wednesday with these ideas of signal space and partitioning, let's say, a set of sets, or partitioning a set into other sets, so that we then end up with sets of signals. So you might look at chapters 1 and 2 of the second textbook to get ready for Wednesday's lecture.